In this lecture, let us complete our discussion on pressure sensors, and then we will move on to a discussion on data acquisition systems. We will discuss about absolute, gauge and differential pressure sensors. To begin with, let us look at absolute pressure sensors. The word sensor may be replaced by a transducer or a gauge. In the literature, you will see that all these terms are used when referring to a device which can measure pressure electronically. An absolute pressure sensor provides a pressure measurement relative to a reference of 0 pressure. Now, it is very difficult to achieve perfectly 0 pressure. So, the pressure is taken as close as possible to vacuum. That is how in a practical configuration it works. So, let us try to see a schematic diagram of the configuration. So, you can see that a pressure is being applied through this port, which is felt by the sensing element on top. So, the sensing element lies here and the pressure is applied from top. At the bottom, you are maintaining near vacuum and therefore, it functions as an absolute pressure sensor. Where are these sensors used? There are a wide range of applications, starting from aerospace to other applications. So, wherever you are talking about elevation above sea level, the preferred choice would be an absolute pressure sensor. Therefore, in altimeters, where you can figure out the altitude of say an aircraft, you use absolute pressure sensors. In weather stations, they are used for measuring barometric pressure. In petrol and diesel engine manifolds, they are used as MAP sensors. So, the engine's electronic control unit uses this information, that means the pressure measurement, to determine optimal combustion of air fuel mix and ignition timing. So, they find a very important use in petrol and diesel engines as well. In industrial applications, widely to develop a partial vacuum. In food packaging industry, to find out residual pressure, to determine the shelf life of the food produce, and the absolute pressure sensor can ensure that the pressure in each package is identically maintained, so that the quality of the food even after long storage would not deteriorate. In industrial applications, they can be used for measurement of very high pressures of the order of few 100 bars. So, there are a wide range of applications. Moving on to the next category, gauge pressure sensor. In this case, again you apply the pressure that you are trying to measure from top onto the sensing element, and you keep the bottom port open to atmosphere. So, atmospheric pressure acts from below and the pressure from top is either higher or lower than PATM. So, the gauge pressure sensor essentially measures the pressure as a differential pressure, that means a difference of pressure between what you are applying and what the atmospheric pressure is at that location. So, if the gauge pressure sensor measures a pressure of 1 bar in a particular vessel to which this port is connected, then essentially the absolute pressure of that vessel would be 1 bar plus another 1 bar, which is because it is being measured with respect to atmospheric pressure, provided the atmospheric pressure in that neighborhood is nearly 1 bar. Otherwise, it works as 1 ATM, whatever it is, which is basically a function of altitude, plus 1 bar. Let us look at differential pressure sensors. Here you are going to measure the pressure difference between 2 points. So, let us say you have connected this port through pressure tubing to a point 1 and again this port to another point 2. So, you are essentially measuring the difference between P 1 and P 2. Differential pressure sensors measure the difference in pressure between 2 points in a system. Where are they applied? They can be used for measurement of flow rate of liquid or gas in pipes or ducts, because the flow rate scales with the pressure drop. The pressure difference helps to detect a blockage in a flow passage or malfunction in a valve. So, if there is a pressure before a valve which is higher than what it is along the direction of flow, there must be something which is blocking the flow between the two measurement points. So, that indicates blockage. In wind tunnel applications, pressure coefficient calculations demand that we measure the stagnation pressure with respect to free stream static pressure, and again the model wall static pressure with respect to free stream static pressure. So, both in the numerator as well as denominator you have differential pressure being applied. In both cases it is with respect to P infinity, that is the free stream static pressure. Hence, the common reference pressure in both the cases is P infinity, and you therefore see the application of differential pressure sensors in this case for measurement of pressure coefficient. So, with that we end our discussion on pressure sensors. Let us move on to data acquisition systems next. So, here what we will do is we will look at some of the important components of a typical data acquisition system, the kind which is usually used for wind tunnel measurements. Depending on the kind of data acquisition system you are using, there may be some differences here and there and some more components which we are not explicitly discussing over here, but we are trying to mention most important ones. A very important and integral part of this whole setup would be the sensor or transducer from which the signal is produced. So, we are talking about an analog output voltage signal which is produced by the sensor or the transducer or the gauge, and in aerospace applications there could be different kinds of gauges which we may be looking at. Typically an electronic pressure gauge, a load cell, an external or internal electronic balances, thermocouples where we are interested in temperature measurement. So, flows where thermal effects are important, hot wire anemometer where we are measuring a turbulent velocity field with hot wire probes. So, there could be miscellaneous sensors applied for measurement of flows, and therefore, you generally have a sensor or transducer which is providing you the analog output voltage which represents a certain physical phenomena. Of course, the sensor needs to be calibrated before it can be meaningfully used for measurement in a wind tunnel. For example, if you are using a sting balance, it has to be calibrated by loading it with known weights and taking the output readings which are recorded by the data acquisition system. So, prior to making wind tunnel measurements, you have to do the calibration by applying weights and loads for calibrating each and every component of the balance. We have discussed this aspect to some extent already, both in the sense of mechanical as well as electronic balances. Now, once you do this calibration, you are likely to obtain a linear variation between the load that you have applied and the output voltage, and the slope of the calibration curve would be in terms of Newton per millivolt, for example. So, if you make a plot to show the data points, you would have the applied load as the independent variable and the output of the balance as the dependent variable. You may have data points like this over a range of loading, and then you would like to have a best fit going through those points, and the slope of that curve would give you so many newtons per millivolt kind of an information, which is basically the calibration constant. So, with this information you should be able to convert, for example, a certain output voltage into a corresponding load. That is the function of this calibration process. So, the sensor needs to be calibrated before it is used. Then we have discussed about scanner, which does the very important operation of multiplexing. It sequentially connects multiple analog signals to one measuring or recording system, where a large number of ports may be scanned sequentially. The next very important entity in a data acquisition system would be an analog signal conditioner. Here, for example, you are showing a picture of a typical analog signal conditioner with 8 channels or so, and the signal that originates at the sensor or transducer is to be fed to this unit, which is the signal conditioner. Depending on how many channels of information you have to process, you choose the number of channels at the signal conditioner end. So, you may be making simultaneous measurements from several channels, and then you need to have supporting number of channels at the signal conditioner. So, in this device, it is transformed into a form which is acceptable to the data acquisition system, which comes next. Here, the signal conditioner circuit helps in achieving the following functionalities. One is amplification of the sensor signal, noise suppression, filtering, excitation of the sensor, zeroing, ranging, calibration, impedance matching. Not that we are going to discuss everything in detail, but let us look at some of the important aspects, some of the important functionalities that a signal conditioner would achieve. So, there are different types of transducers that you may need to handle while you do the measurements. So, we are mostly concentrating our discussion to variable resistance transducers, but we have discussed earlier also that there could be other kinds based on capacitance, reluctance, or piezoelectric kind of transducers, and they have to be appropriately accompanied by corresponding signal conditioners which are compatible with them. This is because the operating principles of the different transducers, they vary. As I said, that we are going to concentrate on variable resistance transducers. So, the circuit of the signal conditioner should be able to handle different configurations at the sensor end. Could be quarter active bridge, half active bridge, 3/4 active bridge, or fully active bridge. Any one configuration it should be able to tackle. How is it done? By using appropriate dummy gauges wherever necessary, whenever it falls short of the full active bridge. Most often, DC excitation is to be provided to the transducer. Depending on what excitation voltage is required at the transducer end, the signal conditioner should be able to provide it. That means, the signal conditioner excitation voltage range should fit to most of the transducers which need to be used along with it. The DC power supplied to the transducer should be very stable. In order to ensure that, you need to have shielded cables used, and the shielded cables should be isolated from the AC lines and other noise sources, in order that you keep high stability in the DC excitation voltage. We will continue with the bullet points at the bottom, and we will go back to the upper part a few minutes later. The Wheatstone bridge should ideally produce 0 output voltage under no load condition, but that rarely happens. There is some amount of gauge to gauge resistance variation, and when you try to install them on the model or the equipment, during the installation also certain residual strain may exist in the gauge, and therefore, the resistance changes. After bridge excitation, due to resistive heating also, there are some changes in the output. There is a warm up phase of the transducers which has to be allowed after the bridge excitation is initiated, so that the bridge shows no further change in output after a certain period of time. Only after that the bridge needs to be balanced, otherwise it will again drift away from 0. So, the 0 offset is nullified in this way. And how is it done? It is done by using a shunt resistance on one side of the bridge. Signal amplification is another very important aspect. Usually the bridge output is in terms of microvolts, because the load related resistance change is very small. It is of the order of 10 raised to the power of -5 to 10 raised to the power -6 ohms sometimes, or most often. Using the common mode rejection principle of differential amplifier, the high signal to noise ratio is achieved. So, you need to maintain a very low noise level. So, there should be appropriate ways by which the noise can be suppressed and minimized. Let us look at what we have on the top part of this slide. So, we have some typical pictures of the front panel of a 2-channel signal conditioner with knobs and indicators which are visible. So, some of the features which are available in a typical standard signal conditioner of this kind are there could be LED displays to show the setup indicator for amplifier balance, bridge balance, a tension compression situation, bridge balance which is to be achieved resistively, gain range and Vernier range which varies the amplifier gain over a wide range. Here in this unit it is between 1 to around 2000. Bridge excitation, as I said, that it varies over a certain range so that it matches the transducer end. Amplifier balance which adjusts amplifier offset, shunt calibration, bridge excitation either on or off, and output of such a signal conditioner can be provided straight away to devices like strip charts, magnetic tapes and XY recorders. If you need to use it to digital data acquisition systems, then you have to convert this analog signal further into a digital one before it is processed. So, you may need to look at analog to digital conversion, so that the analog output of the signal conditioner is converted to a digital one. So, basically the continuous signal is converted to a discrete form. Then you need to look at data cards. So, data cards have a certain data sampling rate per second. Usually sophisticated cards have fairly high data rates, and they could also handle multiple channels of data. Even different kinds of capabilities are built into those different channels, and therefore, there is the provision for simultaneous scanning. Now, if you have a certain total sampling rate, then that has to be divided across channels, and these kind of cards are installed usually into the PCI or PXI slots for data acquisition in a PC. As far as the acquisition rate is concerned, there is a very important aspect that we need to be aware of, that is the Nyquist frequency, which is 1/2 of the sampling rate. So, when the highest frequency of the measured signal is less than Nyquist frequency, then the resultant discrete time sequence is said to be free of a distortion which is called as aliasing. Therefore, you need to go by this recommendation. Adequate data acquisition rate would be vital in situations where you are handling time dependent or unsteady signals, so that you can capture the entire range of frequencies or the entire bandwidth of the signal. When it is very slowly changing with time or it is virtually steady, then the rate at which the data is acquired is not such a crucial issue. But when it is rapidly changing with time, it is essential to acquire the data at very high rates. Additionally, just having high sampling rate at the data acquisition end alone would not be sufficient for this purpose. So, you need to also make an appropriate choice of sensor to support it. So, when we are using pressure sensors, for example, piezoresistive sensors have a much superior frequency response than resistance based sensors, and therefore, they should be chosen for capturing unsteady signals like unsteady pressure fluctuations in a very highly separated turbulent flow. So, here on the right hand side of the slide, you can see typical pictures. The top one is a typical data card which can fit into a PXI slot, and the one which is on the right lower side is showing a typical piezoresistive sensors. So, piezoresistive sensors are based on piezo crystals, which are able to generate output voltage based on the deformation that they undergo under the application of pressure. And the important aspect is that the sensing ports are on the face of the sensor head, and it is recommendable that this face is flush with the surface at which the measurement is made, so that the sensing elements are as close as possible to the source of the unsteady pressure fluctuations. That way the pressure measurements would be most reliable, and you would be able to capture the entire range of frequencies in the signal. So, you need to ensure that the sensing elements are as close as possible to the source in this case. The post processing and analysis of the data that you acquired has to be done through an appropriate software. There are a wide range of softwares which could be used. We have just cited one or two cases here. The post processing software should be easy to use, and it should be reliable and designed for repetitive wind tunnel testing, data collection, storage and analysis. So, if it is to be designed in-house, for example, then appropriate coding has to be implemented, so that we have an software which can support the data which is coming in from the upstream components and can reliably handle it. And also it should be easy to configure the software for the type of experiment or experiments which are planned in the wind tunnel. Some of the software platforms like the NI LabVIEW help provide a virtual instrumentation environment where the programming can be accomplished using modular program elements to form a logical structure in the form of a block diagram, like what you can see over here, and which basically runs in the back end during program execution, and at the front panel which the user sees, the data can be displayed through plots and virtual meters. So, the main issue is that the software should be easy to use, it should be modular in nature, it should be very friendly to the user with a nice graphic user interface. So, these are the trends which are available in the modern softwares. Finally, putting everything together, you basically see a schematic diagram of a complete data acquisition system which comprises of all the elements that we discussed about. So, in a nutshell, if you are having a model inserted in the test section of a wind tunnel, let us say a 2D airfoil model, you may be orienting it to different angles of attack and then immersing it into the flow field, which may be moving at a velocity of u infinity, and again varied over a certain range of velocities. So, for each inclination of the airfoil, you would be interested to measure pressure from so many ports. You may be interested to measure the loads which are coming onto the airfoil model. So, in this case it will be axial force, normal force, pitching moment, etc., which should be measurable using some balance, and then all these electronic signals are first ported into the signal conditioner, and then through a AD converter it is ported into the data card, and then onwards to the PC with the software, where you can post process the results and then obtain the desired outcome from the experiments from the data that you have gathered this way. So, finally, in this lecture we first discussed about the absolute, gauge and differential type pressure sensors. Subsequently, we discussed about different components of a generic electronic data acquisition system which could be used for wind tunnel and associated aerodynamic measurements. Thank you.